Hello everyone, Mr. Froelich here. This screencast will be going through the basics of wind on the planet Earth. Now, in order to understand how wind on the planet Earth behaves, we need to remember that all of the energy in the atmosphere is coming from the sun in the form of radiation. As that light and heat is entering the atmosphere, it's going to do different things, just like the arrows in the energy budget diagram from last week were trying to show. And again, as a review, some of that heat will be trapped by greenhouse gases, which actually ends up being very essential for life on Earth. And from here, what we're going to start focusing on is the convection currents in the atmosphere that end up causing winds on the planet Earth. In order to help visualize how wind on the planet Earth behaves and is formed, we need to understand a few basics about how gas molecules will behave. So this is basically a bunch of dots that are going to represent gas molecules. Now I'm going to ask you a series of questions that goes with this diagram, and I want you to think about the answer while we go through them. So the first question is, which sides are warmer and colder based on just the distribution of the gas molecules? So you'll notice on one side the gas molecules are close together, on the other side the gas molecules are spread out. According to just that, which side would be warmer and which side would be colder? If you said that the left side is cold and the right side is warm, you would be correct. This is simply because the gas laws that we talked about before school was closed, describing that when you warm up a gas, its volume will increase, making it spread out. And of course, the opposite will happen when you cool it down. That makes the volume of that gas go down, and the gas molecules get closer together. Next question. Which sides have a higher and lower density of gas molecules? So again, you're just looking at the distribution of the gas molecules themselves, which side is higher and which side is lower density. If you had the more dense side on the left and the lower density or less dense side on the right, you would be correct. Again, think about what the definition of density is. Density is just describing how closely packed molecules are. So the more molecules in a certain area or certain volume, the higher the density. Question number 3. Which sides have higher and lower pressure just due to the air? So which side would have a higher air pressure and which side would have a lower air pressure? If you said that the higher pressure is on the left side and the lower pressure is on the left side, you would be correct. Again, pressure in this case is just talking about the physical amount of molecules. The more molecules that you have interacting with you, the higher the pressure in that area. So far, I know that you are 3 for 3 on these questions. This is where they start to become related. Right now, these gas molecules are stationary. They are not moving. So if we allowed them to move, which way would those air molecules begin to naturally flow? If you said that those gas molecules would move over to the right side, you would be correct, 4 for 4. Now, the reasoning behind this can be explained in several different ways. The easiest way to explain why the gas molecules would be moved in this direction is to think back to what I said 1 million times before school was closed. Pressure always goes from high to low. So in this case, my higher pressure on the left is going to naturally try to flow over to the lower pressure on the right. Now, as you can probably imagine, there's going to be a point in time where these gas molecules no longer want to move. So when will they stop moving is my next question. If you said that the gas molecules will stop moving when the pressure is balanced, you would be correct. Now, I only have one more question for you, okay? Now, when those gas molecules are moving from one side to the other, That movement of air is called, you guessed it, wind. I know that you knew all of these answers as we went through this, and you are super smart. I'm very proud of you. So, in order to understand wind, we need to look back and we need to think of some basics. Wind is simply the movement of air from one spot to the other, and that movement only happens because some parts of Earth are getting more heat than other parts of Earth. It's not hard to realize that in Minnesota, we don't get as much heat or much solar energy as, let's say, Mexico or Florida or Arizona, places that are warmer. That sets up uneven heating on the planet Earth. When we are going to label winds, which we will start doing later on this unit, we're always going to label from where they come from. So for example, a wind that is blowing from west to east is going to be called a westerly wind. Winds that come from the north will be a northerly wind. We're always going to describe where it's coming from. The strength or speed of that wind depends on the difference in temperature and difference in pressure between two areas. So if I have one area that's very cold and one area that's very warm, the pressure in those areas is going to be very different, and the wind between those areas is going to be stronger because the air wants to move from the hot area to the cold area very, very quickly. This can also be explained or visualized by thinking back to the red and blue water demo that I did in last week's videos. Okay? Since I had the boiling water on one side and the cold water on the other, I created uneven heating in that bin. And I colored the water so that you could see the flow, and you saw that instead of just mixing randomly, it started to swirl around in a circular pattern similar to a convection current. To help us understand convection currents, I have this little diagram here, which is a very simplified version of how wind works. You'll notice on the left side, where it is over land, it's warmer. And it's purely warmer because the land will absorb more of that heat, that air will rise, and it will create low pressure. On the right side, over the water, more of that light is reflected, which means the temperature will go down. It's not absorbing as much. And as the temperature goes down, the air will cool and sink, which creates a high pressure center. So now I have a warm area and a cold area. Uneven heating. I have a low pressure and a high pressure area, which is a difference in pressure, and as a result, we start to get a circulation of the air. Now, if you look at my super cool stick figure Mr. Fro, if you were standing in that spot, A, you would be having fun at the beach, and B, you would be feeling the gust of wind blowing past you because there's a difference in pressure and temperature in this area. One way to start to examine how global winds function is to look at how energy and light is distributed across the planet. Now, we already discussed the energy budget last week. That's an entire global average and no longer applies to certain situations or locations. So each spot is going to have a different set of numbers for that diagram based on where they are on the planet Earth. So now this question is asking you to examine the picture, point A, B, and C, which one receives the most direct sunlight? And in this case, we mean direct as in the most energy. If you realized that the equator is receiving the most direct light and the north and south poles, or point A and point C, are receiving the least amount of energy, you would be correct. Think of it this way. If you took a flashlight and you shine it straight down at the ground, you'll see the circle that it makes. If you take that same flashlight, the same distance from the ground, and you tilt it, instead what you see is that same amount of light spread out over a larger area, and it seems to dim everything that it's touching. Now, you did not change the brightness of your flashlight. What you did is you took the same amount of light emitted and spread it out. That's what's happening at point A and point C, and as a result, they'll get less heat energy. So point A and point C, because they are farther away from the equator, receive less solar heat. So to visualize how this would set up global winds, we can look at this diagram, which is again a simplified version of what winds tend to do. So I would have my cold air at the North and South Pole. I would have my warm air at the equator, just like we were explaining in the previous diagram. And what this does is it sets up rising air at the equator and sinking air at the poles to create these global convection cells all across the planet. Now, if you look closely, this is a decent example to visualize how wind is formed, but it's a poor example to explain how wind behaves across the planet. Because according to this, in Minnesota, our winds will travel in one direction in a straight line from the north every single day. Now, it doesn't take someone who pays attention to the weather to realize that that is not always the case. Every single day, the wind will change direction and change strength. So there has to be something else going on to make wind change. That would be the Coriolis effect. The Coriolis effect now brings in another element to the behavior of wind. It says that winds that would usually go in a straight line are bent because Earth is rotating underneath them. So you have to remember that as the Earth spins once per day, winds and water are flowing free of that because they're not solid. And what this does is it makes them seem to have a bent path instead of a straight line. Think back to when you've maybe seen images or time lapses of a hurricane. If the Earth was not spinning, a hurricane would not spin either. Because the Earth is rotating, it makes the winds around a hurricane spin in a certain pattern. And that pattern depends on which hemisphere you are on. In the north, the air, as it's moving, is deflected to the right. So whatever direction it's moving, it gets bent over to the right. It gets sort of turned around. In the south, that air is deflected to the left. And that's simply because in the south, the Earth is spinning sort of the opposite way because you're kind of thinking you're upside down. Now, the time frame of this motion is the thing that's key. It does not happen in small scale situations. It only works because since Earth is moving once per day, large scale oceans and wind and storm patterns will be affected. Okay? Now, this is a very hard concept to picture in your head. There's almost no way that I can explain it to you that will allow you to visualize what's going on. So what I'm going to do after this screencast is link to a YouTube video that does a very good job at explaining and showing how this works. So while you watch that YouTube video, pay attention to the camera angles and the way that they show how the objects are being bent in their examples, and relate that back to the way air is bent or deflected based on the rotation of Earth. If you have any questions on the material of this screencast, feel free to send me a message in Schoology or bop into the Google Meet that I have every day from 10 until 11:30. The link is in the main page of Schoology. I hope that you have a great rest of your day, and thank you for watching.